Hello, happy Friday. So, we are going to do lecture 10, and this will be the last lecture for quiz 2. Quiz 2 will cover lecture 6 through lecture 10. A brief review from last lecture. We talked about radar pointing direction. We talked about the elevation and the azimuth. So the elevation is how high up off the ground the beam is, and the azimuth is the angle around the radar. We talked about radar scan types. RHI is scanning up and down at a fixed azimuth, and we don't really do this one. We use PPI, which means the radar is scanning in a circle at a fixed elevation. A volume scan has multiple PPIs at different elevation angles, and it takes an entire snapshot of the atmosphere from the lowest volume scan, or the lowest PPI, to the highest one. The volume coverage pattern, the VCP, is what elevations are used in a given volume scan. So some volume scans emphasize the lower levels, especially during a severe weather. They will have the lowest levels scanned multiple times, and they will also go up the entire atmosphere and have more coverage. They will also scan the atmosphere quicker than they do in a clear sky day or a light rain day. Some of the limitations of the radar include ground clutter, non-meteorological targets, ducting, Earth's curvature, beam blockage, beam spreading, and sunstrobes. Now let's get into the fun stuff. Oops. Spoiled it. Okay. Thunderstorms overview. Lightning and thunder. So, at any given moment, there are 2,000 thunderstorms active around the world, on average, and around 45,000 thunderstorms occur worldwide each day. Hopefully one of those occurs here today. Well, I'm recording this on Wednesday. Really hoping that happens for us. Might happen a little bit later on. These thunderstorms typically occur in the low latitudes. It adds up to over 16 million storms per year, and about 10,000 of these storms occur in the United States. The reason why they happen in low latitudes is because at the equator you have a lot of rising motion, you have warm water, very good for thunderstorm formation and creating unstable air masses. So, most thunderstorms occur in the low latitudes, especially around the Intertropical Convergence Zone, ITCZ. Winds converge at the surface and they rise. So the rising motion leads to the parcels cooling. Then they saturate, they form clouds, and then they form precipitation. The low latitudes are warm and moist. Maritime equatorial. Did you hear that? Is that my cat? Maritime equatorial and maritime tropical, which is the least dense type of air. Because equatorial and tropical air is warm, and maritime means it's moist. Moist air and warm air rises. In the United States, thunderstorms also occur most often where air is warm and moist. The Gulf Coast and the Southeast. So you can see that big blip in Florida, surrounded by water on all sides. Near Lake Okeechobee. Florida is called the Sunshine State, but that's for tourism. It's not true. But as you can see, the Deep South has the largest number of thunderstorms. You also get a lot of thunderstorms in New Mexico. And this is because New Mexico has a monsoon season. And in the Rocky Mountains on the the western side of the Rockies, you have air that is forced to orographically lift and rise, and this air gets wrung out and becomes storms. So this map shows the number of days with thunderstorms per year. In Oklahoma, we get about 50. I guess we used up most of ours already because I don't know. I'm still waiting. I have high hopes today on this Wednesday that we might get a little rain. I really hope. I guess if you're watching this on Friday, you'll know. So there's two different types of thunderstorms, two categories. There are ordinary thunderstorms. These are also known as pulse thunderstorms. I think that's a cooler name. Pulse storm. So these are just typical thunderstorms. They last 30 minutes to an hour. They don't produce damaging hail, damaging winds, or tornadoes, but they can cause flooding and produce small hail. So these pulse thunderstorms are kind of what you find in the summer. So you get warm air at the surface, it evaporates, it goes up into the atmosphere, it condenses, and it condenses enough to form raindrops, and the raindrops fall down. And that's about it for this storm. Very simple process and does not last long. Severe thunderstorms, on the other hand, persist for hours, and they do produce damaging hail, damaging winds, and or tornadoes. So the first one, the pulse storm, is more of a convective process that forms from surface-based convection, while the severe thunderstorms usually have a front associated with it that generates that extra lift. All thunderstorms produce thunder and lightning, and that's how they get their name. How does the National Weather Service define a severe thunderstorm? Are they going to tell us on the next page? 58 mile per hour winds, 1 inch hail, or a tornado. 1 inch diameter hail or greater, quarter size hail. Wind gusts greater than 58 miles per hour, greater than or equal to 58 miles per hour. So 50 knots, or a tornado. Asterisk, why? Why? Why is it covered up? I have a feeling I know what it says. It can have any of these. Yes, only one of these has to be true. So even if a storm doesn't have 1 inch hail or 58 mile per hour winds, if it has a tornado, it's severe. Likewise, if it has a 1 inch diameter hail, but it doesn't have the other two factors, it's a severe storm. So you only need one of these for this thunderstorm to be severe. So what are the ingredients for thunderstorm formation? You can remember this with the acronym SLIM. Shear, lift, instability, and moisture. So the last three are what produce ordinary thunderstorms. You don't need vertical wind shear to produce a severe storm. Or no, you don't need vertical wind shear to produce a pulse storm. You need vertical wind shear to produce a severe storm. That vertical wind shear is what is going to create like the hail profile, the wind profile that you need for that, and also it's what generates tornadoes. So you need all four of these to create a severe thunderstorm, and only the bottom three, lift, instability, and moisture, to create a pulse thunderstorm. We should take a warm, moist air and push it somewhere else. Moisture. Thunderstorms form primarily in warm, moist air masses. This is the least dense type of air, like we've talked about. It rises easily and rising air creates clouds, precipitation, and storms. For the United States, this usually means a maritime tropical air mass, and they come from the Gulf of Mexico, the southern Atlantic, and the southern Pacific. For Oklahoma, the maritime tropical air masses are advected northward from the Gulf of Mexico. Advection, we talked about this. This just means wind blowing a property from one place to another. So the moist tropical air mass is advected from the Gulf of Mexico to Oklahoma by the wind. Again, talking about moisture, this is going up the atmosphere on the right. So advection, again, is wind blowing an atmospheric property from one place to another. So you're going to look for these wind barbs crossing the isotherms, which means temperature advection, and or isodrosotherms, which is moisture advection. So the isotherms mean lines of constant temperature, isodrosotherms mean lines of constant moisture. So if you can get these wind barbs to cross over them, that means that they're infecting one property air into another property air. So if you can get the wind to blow from the moist air into the dry air, or from the cold air into the warm air, it can generate lift. Or from the dry air into the moist air. It just depends on the setup you have. We talked about fronts earlier. So this is warm air advection down at the bottom. So think of these as isotherms. So these are lines of constant temperature. The wind barbs are crossing the lines of constant temperature and they're blowing from warm to cold. So that's warm air advection. Good for like stratiform storms. Cold air advection is good for the severe weather outlooks and mesoscale convective systems, MCSs. So you have cold air blowing into warm air, and that's going to force that warm air to rise. No temperature advection is when they run parallel to the isotherms. So warm blowing into warm, cold blowing into cold. There's no temperature advection. The temperature is staying the same. You want this change from cold to warm, of cold into warm. So I guess it goes from warm to cold. But yeah, cold blowing into warm, this is the best for severe weather setup. But you can also get a thunderstorm from warm air advection as well. Again, advection is wind blowing an atmospheric property from one place to another. So you look for wind barbs crossing the isotherms, which is temperature advection, or isodrosotherms, which is moisture advection. So here we have a cold front moving through, and as you can see, I think this is at the surface. Yeah, yeah. Close to it. No, maybe not. I don't know what level this is at. They cut it off. Anyway, what's happening here is you can see these wind barbs, and these are your isotherms. So these are iso heights, isotax, iso heights. These are lines of constant height. It doesn't really matter. It's associated with temperature as well. So anyway, what's happening is you have this cold air right here, and it's blowing this cold air, so it's coming from the cold air, and it's blowing into the warm air. So this is cold air advection in this direction. So it's coming from the north, moving south, cold air advection. Let me know if that doesn't make sense to you. You can send me an email. But yeah, cold air blowing into warm air. Cold air advection. Another ingredient for thunderstorm formation is lift. Rising motion, lift, is necessary for air parcels to cool their dew points and reach saturation, cool to their dew points and reach saturation, to form clouds and precipitation. So there's different ways that you can achieve this lift. If you have a front, it can force the parcel upwards, Likewise, if you have a dry line, it's dense air and it can push your parcel upwards. And if you have a low pressure center, that's usually formed from divergence aloft. What? If you have divergence aloft, it will force air upwards. May I help you? Weak rising motion primarily forms ordinary thunderstorms. It's most likely to form away from fronts, dry lines, and low pressure centers, where lift is weakest. Don't drink my water. Strong rising motion primarily forms severe thunderstorms. More likely to form... You're covering my screen. Come here, baby. It's more likely to form along fronts and dry lines near low pressure centers where lift is the strongest. What? What can I do for you? You better not eat the thumbtack. Okay. We went over this diagram before. This is the unstable. So, this red one right here is the red parcel. This blue one is this red one is the environment temperature. This blue one is the air parcel. So the air parcel temperature at the surface to about this level right here, is warmer than the environment, so it's going to rise. And then this is where they're equal, and then it's stable up here. Stop! Thank you. It's stable up here because the parcel is colder than the environment. So it's unstable, neutral, stable. So less stable means that the air rises more easily, and more stable means that the air cannot rise as easily, and it has to be forced up somehow, which is hard. It can happen, but it's harder to do. It's not going to do it on its own. If the air parcel is warmer than the environment at a given level, the atmosphere is unstable. Unstable atmosphere is the best for thunderstorm formation. So, vertical wind shear is another ingredient. So the first three ingredients, moisture, lift, and instability, are required for all thunderstorms. Get down, get down. No, nope. Come on. Hey, good boy. They're required for all thunderstorms. You need moisture, lift, and instability for every type of thunderstorm. But for severe thunderstorms, you need another component, which is vertical wind shear. You need it to change speed and direction with height. In the vertical, yes, with height. That's vertical wind shear. Please stop. Stop. Okay. Sorry. I probably shouldn't have let him in here. Yeah. So this is from last lecture. So we talked about directional shear and speed shear. So vertical shear is the change in the wind speed and or direction with height above the ground, as we talked about. So speed shear is this one on the right, and it just means the wind speed is increasing or decreasing with height. And the directional shear means that the winds are changing direction with height. Are you sweet? You're a good cat. I love you. I'm sorry. We'll hang out after this. Okay. Formation of a thunderstorm. So, I think we went over this, but we went over parcel theory, that's for sure. So, you have warm, moist air parcels that start at the ground. And then they rise upward, which is convection. And they expand because the pressure is less aloft, and that causes cooling because the particles aren't as tightly packed together and the particles don't move as fast. So the updraft is this column of rising air parcel that support a cloud. So they move between 5 miles per hour and 125. That is really strong. I don't know if I've ever seen an updraft at 125 miles per hour, but I'm sure it exists in an extreme situation. So the updraft is the first part of a thunderstorm to develop, and it's not sufficient on its own to define a precipitating cloud as a thunderstorm. So a cloud forms after the air parcels in the updraft rise far enough to cool to their dew point and reach saturation. The updraft supports the cloud by continuously supplying warm, moist air parcels. Stop it, dude. Dude, no thumbtack. The updraft supports the cloud by continuously supplying warm, moist air parcels that can easily reach saturation and condense. Precipitation may form within the cloud as it grows. As precipitation grows, it gets heavier and it falls out. So whenever this force of this updraft can't support the weight of the precipitation, so the force of gravity is mass times the gravity. So once the mass of these raindrops becomes too heavy, the precipitation falls. If you have a stronger updraft, it can support larger precipitation, or even hail. The falling precipitation creates a downdraft. A downdraft is a column of descending, often rainy and cool air. It's created by raindrops quite literally dragging the air down. No! 1 second, I have to kick my cat out of my room. It's not. He can't control himself. He's a baby. Come here. Come on. Yeah. Leave. Okay. Sorry about that. I love him a lot, and we spend a lot of time together. But sometimes he just can't control himself. So an example of a downdraft that you might be able to feel in real life, if you ever like stand next to a waterfall, turn on the shower, turn on your sink, or if you have fast moving water, you can feel the downdraft. So it's just this air that's being pushed down in the column of water. So the water is descending and it's creating its own wind. So then what? When the descending air hits the ground, it has to go somewhere. So it hits the ground, it diverges, and it's called outflow. This outflow produces the gusty, often cool winds that flow out of thunderstorms. This is known as the cold pool. So usually it's colder than the surrounding environment. And it's due to the evaporation of rain in the downdraft, which cools the air. So remember, evaporation is a cooling process. So if you have rain on the ground, it evaporates, and that creates a cold pool. The leading edge of this outflow is called the outflow boundary. So you can see it's this yellow dashed line here. So if this storm is moving towards us, this is the edge of the outflow. And this is where it has the strongest surface winds in a thunderstorm. The outflow is a lifting mechanism. Yeah, because what happens is you have this cold flow right here, and it gets up under this warm air, so it can trigger more rising motion. But usually if a severe storm becomes outflow dominant, it's not really a good thing, because that means that you can't really support this updraft anymore. But sometimes the outflow boundary can trigger new storms. So the thunderstorm type, ordinary or severe, depends on where the downdraft falls relative to the updraft. So this is balanced by the strength of the rising motion and the strength of the vertical wind shear. So in an ordinary thunderstorm, there's not really any shear like we talked about. So there's not, the updraft strength is going to be stronger than the strength of the shear because there is none. There usually is some, but not much. Like, it's not going to be a predominant factor in storm formation. So the updraft will rise straight upwards. It's not being pushed or tilted in any way. It's not being twisted. It's just straight up. Downdrafts will fall straight down through the updraft, and the downdraft and the updraft are aligned. Not good. So this is contamination, and it will prevent future rising motion because these two air masses, or not air masses, but temperatures of air are mixing. You don't want these aligned to keep a storm going. Because the updraft and the downdraft are aligned, the descending air in the downdraft suppresses the rising air in the updraft, so this causes the storm to dissipate and die. So it if you have the updraft weakened, it's not going to be able to support this anymore. So usually in the decaying stage of a storm, the storm will be more powerful and dump more rain because the updraft dies, so all of the rain just falls out of the cloud. So here are the stages of the pulse thunderstorm, the ordinary thunderstorm. So you first start in the cumulus stage. This takes about 10 minutes. It's just the updraft. There's no downdraft yet because the precipitation has not formed, so there's no lightning or thunder either. Then, after about 10 minutes or so, the storm reaches its mature stage. So the updraft and the downdraft are both present. It doesn't look like it in this diagram, but the updraft and the downdraft are aligned, and the air is descending through the updraft. Precipitation forms and falls to the ground, and at this stage you get lightning, thunder, and gusty winds. And then in the dissipating stage, misleading because it's the rain is strongest in this time period. The updraft decays and the downdraft continues to fall through and weaken it. So this is where you get this strong storm. Eventually the precipitation will stop once it's rained itself out, and the cloud will evaporate. Okay, for a severe thunderstorm, you have vertical speed shear, and you usually have vertical rotational shear. So the wind speed is increasing with height. So we start with 5 knots at the surface, 30 knots aloft, so you get this tilt. So the updraft is tilted. This is speed shear because it's easiest to see, but it's kind of a similar concept for directional shear. So yeah, directional shear can really get these things to rotate. And they can also move the updraft and downdraft. They can cause tilting. But speed shear is like pretty direct in the way it does it. Herein, the winds increase in speed with height. Moderate to strong vertical wind shear of either type, asterisk, tilts the updraft away from the vertical. Okay, so see, it's not in the vertical anymore. If the rising motion is too weak, the shear will be much greater than the updraft speed, and the updraft will tip over, so the storm will dissipate before it even begins. We like to call these turkey towers. Literally, the top of the storm will just get shaved off. If the rising motion and the vertical shear are balanced, the updraft will persist. So you want the updraft and the vertical shear to be in balance. The vertical shear tilts the updraft away from the vertical without tipping the developing storm over. So you don't want it to tip over, but it's good if it's got this angle to it, if it's rising at an angle. This is to prevent the contamination. If the rising motion and vertical shear are balanced, The updraft will persist, and the vertical wind shear tilts the updraft away from the vertical without tipping the developing storm over. Then, as the storm develops, it creates a downdraft, and the updraft and downdraft are not contaminating each other. And so the storm can persist for longer because it's not contaminating its fuel. So the storm persists, and it can eventually become severe. So the severe thunderstorm, the outflow can actually strengthen the updraft. So this is what we were talking about. So you have this outflow. This is the cold pool, and the outflow causes this cool layer to move in at the surface. And what happens is that cool air forces this warm air to rise, because warm air rises, and this updraft air is warmer than this cold pool air, so you get increased convection. So it enhances convergence underneath the updraft, and it promotes more rising motion. Yep. With all of these processes working together to sustain and enhance the updraft, severe thunderstorms can persist for hours. So the takeaway is that a balance between vertical wind shear and rising motion produces severe thunderstorms. This is fun. This is the formation of a thunderstorm chart. So this is what you get. You get. We haven't talked about like any of this, so I don't think I should talk about this yet. But you can look at this. This is nice. This is nice. But this is the updraft. A tornado is a rotating updraft. That is why the directional shear is very important, because you need to get the updraft rotating. And this is the downdraft, and you can see they're not contaminating each other. And here's the boundary, and it's pushing up this storm. This cold pool boundary. It's adding extra oomph. This thing is rotating so hard that it's pulling this rain around to the back. And this rain in the back also gets up under the tornado, and it will create more lift, or under the updraft if no tornado is present. So you get lift on both sides. It's warm right here, and so it's just a storm that sustains itself. Okay, so we talked about thunderstorm basic facts and trivia. We talked about ingredients for thunderstorm formation and the acronym SLIM. And we talked about the formation of ordinary or pulse thunderstorms and severe thunderstorms. And we looked at this diagram. You can look at it real good, and this is a diagram that you will come across a lot in meteorology. I don't know if they're going to want us to talk more about this diagram. Probably, so we'll get to that if we get to that. Yes. So we're going to talk about how to identify thunderstorm structures. So we've discussed the updraft, the downdraft, and the outflow. So we're going to talk about the cloud base, the inflow, the anvil clouds, overshooting tops, outflow boundaries, and shelf clouds. This is really cute. I like this. This is a supercell. So, precipitation and cloud base. So the cloud base below an updraft is usually rain-free, and the cloud base below the downdraft is full of precipitation. About the cloud base, to get a severe thunderstorm that produces a tornado, you want the cloud base to be low enough to the ground so that the tornado doesn't have to travel a very long way to get to the ground. So if you have a low cloud base, that is good for tornado formation. Whoa, 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 whoa. Oh, nice. Okay, this is a dry microburst. That's beautiful. Look at that. That is so distinct. Like, it's well defined. Where is this from? What? A blade system? That ain't my field. Okay, anyway. So, many downdrafts are filled with precip, therefore they are dark, and they are easy to see. Some downdrafts are only filled with a few large raindrops, and the cloud base below may appear clear even though there is rain. This type of downdraft is called a clear slot. So I guess over here on the left, there's like some clear slotting going on. A downburst is an area of strong, often damaging winds produced by one or more convective downdrafts. So a microburst is a downburst that's less than 4 kilometers in horizontal scale, and a macroburst is greater than 4 kilometers in horizontal scale. So this is a microburst. This is a dry microburst. You can tell it's dry because the air around it is super dry and it's really well defined. So this is probably in the desert somewhere. And it's just dumping. This is just a huge downdraft that's dumping a bunch of water. And the updraft is probably over here somewhere. Or it might be contaminated. We don't really know. I would say that the updraft is probably right here on the left. And it might be rotating and pulling this air right here down as well. But I don't know because I haven't really looked at it. I'm just looking at a picture of it, so it's hard to tell. Anyway, the inflow is the air that's pulled along the ground and flows up into thunderstorms. You want warm inflow. It's good fuel. So typically the inflow is southerly or southeasterly boundary layer air, which is warm because it's coming from the south. Upon reaching the updraft, it turns sharply upwards and becomes part of the updraft. So it enters the rain-free part of the cloud base. So imagine that this direction is south and it's pulling this air from the south up into the updraft. If the inflow is warm and moist, it supports rising motion since the air is positively buoyant. It helps the updraft persist. Yes, so if you're pulling in warm, moist air, it's going to help it to rise more. In severe thunderstorms, the wind speeds along the ground in the inflow can reach 30 to 40 miles per hour. This is true. They said 125 miles per hour on the earlier slide, which seemed like a stretch, but I don't know. That's probably going to be an extreme case. But yeah, 30 to 40 miles per hour, like, it can happen. You can get updrafts at that speed. Warm, moist air may cool as it rises into the updraft. So it may reach saturation quickly and condense into a long line of clouds that lead directly into the updraft. This is called beaver tail clouds. Basically, it's a little complicated, but there's like the pressure drops, and because the air is moving quickly, and the pressure drop causes condensation because pressure decreasing cools the air. So it creates like this little tail in the inflow. It's just because the wind speed is fast and it causes condensation. So these clouds help us visualize where the inflow leads into the updraft of the thunderstorm. So if you see this little tail here, that just means it's an inflow tail. That's what we call it, an inflow tail, but they're calling it a beaver tail. Anvil clouds, these look like sock puppets. This is what you see in a severe weather situation, is these sock puppet looking clouds. So this forms when the storm clouds hit the tropopause and spread out. So yes, at the tropopause, the temperature starts to increase as you go up into the stratosphere, so it can't really go over the top of the tropopause much. Instead, it will spread out, and it will look like this anvil. And this air above it is stable. So this shows us where the troposphere ends, and up here, it's very cold up here, so it's made up of ice crystals, and it's definitely below freezing up there. So you can tell where what the clouds are primarily made of based on looking at them. So in ice, the edges look fuzzy. This is because the ice crystals kind of get blown around easily up there, and then the edges look sharp where it's water. So this is probably about the Bergeron line, where it's 0 degrees Celsius around here, and you kind of have all 3 states of water existing at this place, and then it turns to ice. So there's something called an overshooting top, and this is at your updraft. So if you can get your rising air to be, hit the tropopause with enough force, it can kind of push up into the stratosphere a little bit, and this is called an overshooting top. So usually only updrafts and strong storms have air moving fast enough to do this. But you can see it. You can see it on satellite sometimes. So this is just like in the anvil cloud when it's a really powerful updraft, you can get an overshooting top. The definition is a dome-like protrusion above an anvil representing the intrusion of an updraft through the tropopause. So it just looks like a little bump on the top of the anvil. So the overshooting top looks crisp, so it must be made of mostly water. And this is because water takes time to freeze, and it's moving so quickly that it doesn't have time to freeze before they hit the tropopause. So it's a good indicator of a severe storm. So yeah, water takes time to cool off and freeze. It doesn't freeze instantly. Like if you put an ice cube tray in the freezer, it's not going to instantly freeze. It takes time. And it's the same with clouds. If you have a fast updraft, it's not going to have enough time to freeze before it hits the tropopause. So that's why overshooting tops are defined. Even though this picture is like, I don't know, it probably has like 6 pixels in it. Okay. Here's a vertical cross-section through a storm with an overshooting top, a radar image of the storm with the same cross-section noted. Okay, so this is the storm. We're looking down at it, and they're cutting across from A to B, so they're cutting through this core here, which is probably a hail core. This is what it looks like if you were to like open it up and look at it from the side. This is what it looks like. So we're at like 15 kilometers or so. This is where the tropopause is, 16 kilometers. It's going past the tropopause. It rises above the tropopause. Okay, outflow boundaries. We talked about these. So along the outflow boundary, there's convergence, and it enhances the rising motion ahead of the thunderstorm. This is an important lifting mechanism. It can help the parent storm strengthen, and it can cause new storms to form. Oh, by the way, this is the people who made these diagrams on the last page are in our department. Dr. Cameron Homeyer and Elisa Murillo. Oh, Elisa? Eliza? Elisa. Yes. You can talk to them if you want to know more about this, because they made them. Okay. Yeah, so this is an important lifting mechanism. We talked about it. It can help the parent storm to strengthen, and it also can cause new storms to form. They're called gust fronts, and because of the strong winds that happen at the outflow boundary, they can push air up. And since this air is relatively cold, sometimes you'll see a cold front symbol at the outflow boundary location to signify a miniature cold front. Wow, that's a really nice outflow boundary. Wow. Okay, yeah, you can usually see them on radar. Not this nice, but the air often picks up and pushes along bugs, dirt, and debris as it advances, and this can appear on radar. It's the fine line of reflectivity ahead of the storm. So usually you don't have like a full circle like this, but you will have like a boundary that's moving with it, and that's where the outflow boundary is. You want the outflow boundary to be close enough to the storm. When it gets too far away from the storm, that's when you know it's time to go home, like pack up ship. So like up here, for instance, like it's really far from the storm, so it's not really going to help it. But when you have an outflow boundary that's close to the storm, that's good. And that will help generate more lift for the storm. A shelf cloud. This is a nice shelf. It's a long flat clouds that extend out from storms along the outflow boundaries. Shelf clouds are a warning. They let you know that a strong storm is headed your way. Usually you'll have 5 to 10 minutes to get inside after a shelf cloud passes before the storm gets here. We like to call this the whale's mouth because, like, this looks like a whale and this looks like the weird, like, whale teeth. So if we call these the whale's mouth. And there's a video of one. Yeah, shelf cloud, they look cool. They don't necessarily mean there's going to be a tornado, but usually it's going to rain hard if you have one of these. Storm organization. Thunderstorms can be categorized further beyond just ordinary and severe. Ordinary storms may be isolated from one another, so you'll have single cell thunderstorms or supercells if their updrafts are rotating. So a single cell thunderstorm doesn't have a rotating updraft. A supercell has a rotating updraft. And supercells can form tornadoes, but it doesn't necessarily have to have a tornado to be a supercell. Or they can be grouped together in multi-cell clusters. They can also form lines, which are called MCSs, or bow echoes. We've talked about those in this class. So each single cell thunderstorm is usually isolated from the next, usually tens of kilometers away, and they typically form in the summertime afternoon, after the sun has heated the ground and the warm parcels of air are freely rising from the surface. So this is the ordinary or pulse thunderstorm we were talking about. It just looks like a regular storm. They last about 30 minutes to an hour, and they can produce flooding or small hail at the worst. So this kind of looks like Florida. Like, I don't know. Florida gets a lot of these pulse type storms, but these are just formed from summer convection. They don't do all that much. They just rain and have thunder and lightning. Multi-cell storms are clusters of ordinary thunderstorms. All of the individual storms that are part of a multi-cell cluster are at different stages in their life cycle. Since multiple storms are competing with each other for warm, moist inflow air, none of them are able to become severe. Instead, they all stay ordinary. But flooding is likely if these storms pass over the same location in succession in a short period of time. So this is called training. So if you have a storm that keeps passing over the area or whatever, it's just called training. Yeah, so they just like mush up together, and they can last a little longer because they're bigger, but not as long as like a supercell because they're super contaminated. Supercells and MCSs. So these are two other types of storms. Yes. Oh, okay, we're gonna wait on these, and we'll learn more about them next week. Well, maybe we'll learn about them today. I don't know if the PowerPoint is covered today or next week. But supercells and mesoscale convective systems deserve their own lecture because they're awesome. Okay, let's check. Okay. Yeah, it will be next week. We're going to talk about lightning and thunder today, which is equally cool. I mean, maybe not equally. Supercells are like the bread and butter of meteorology, but lightning and thunder is cool too. So we just talked about thunderstorm structures. So we talked about precip and cloud base. We talked about inflow. We talked about the anvil. We talked about overshooting tops, outflow boundaries, and shelf clouds. Then we talked about single cell, multi-cell, and then we said we're leaving the supercell and MCS for next week. Let's talk about lightning and thunder. Atoms and ions. So everything is made of atoms. I was watching a Vsauce video yesterday. Let me look it up. I wrote it down. Wait, hold up. Don't leave. The Earth has 100 quindecillion atoms, which is 10 to the 50 atoms. So 10 times 10 to the 50th power. So that's a lot of zeros. That's 50 zeros. That's a lot. Anyway, fun fact. But atoms have 3 components: protons, neutrons, and electrons. And protons are positive, Electrons are negative and neutrons are neutral charges. And if the number of protons is not equal to the number of electrons, the atom becomes charged and it's called an ion. So if it has more protons, it is positively charged, and it has more electrons, it is negatively charged. So if an object is positively charged, it has more positively charged ions than negatively charged ions. And then if an object is negatively charged, it has more negatively charged ions than positively charged ions. And objects of opposite charge attract each other, while objects of the same charge repel each other. So an electric current is the flow of electric charge between two objects. Electrons flow easily towards positively charged particles or objects. That's because electrons are negative. And protons, which are positive, flow towards negatively charged particles or objects. But it takes more work. Yeah, electrons, they're on the outside, while protons are kind of like glued to the neutrons in the center. So that's why it's easy for electrons to move. They're just moving around real fast and they're tiny. But protons are kind of bigger, they're more massive, and they're kind of glued to these neutrons, so it takes more effort to get the protons to move. But you can. So static electricity is simply just the buildup of electrons on the surface of an object. So it builds up when the object is surrounded by an insulator, a medium that doesn't allow electrons to flow freely. The air is an insulator. So when enough electrons build up, they will discharge towards any positively charged object, even across an insulator like air. So like if you were to shuffle your feet on the carpet, what happens is you have like the electrons that build up on your skin, and it's released onto the objects that you touch. So your body's like, oh, we're not in balance, and it wants to give some electrons away because you have a negative charge. You pick up a negative charge, so it wants to give it away. So lightning works in a similar way. Are they going to show the lightning picture? Okay, yeah, they're going to get to it. I just wanted to make sure. So the Earth has a fair weather electric field. This is the electric field in the absence of clouds. So typically the atmosphere is positively charged while the surface is negatively charged. The fair weather electric field does not have a large enough buildup of electrons to produce an electric discharge. So yeah, there's not really like anything, like if that was the case, if there was a strong enough electric field to create a discharge, that means we would have lightning and clear air. So that would be weird and unsafe. So fortunately that is not the case. But the condensation of water does lead to a larger buildup of static electricity on the surfaces of water droplets in the clouds. Since storms experience the greatest amount of condensation of any clouds, they have the biggest buildup of static electricity of all cloud types. Storms are the only clouds that can cause enough buildup of static electricity to produce lightning. What is lightning? Lightning is an electric discharge that occurs due to a massive buildup of static electricity in the clouds. Thunder is the sound waves created by lightning discharges. So, you can't have thunder without lightning. Thunder is the sound of lightning. And lightning is incredibly hot. And what happens is the air explodes. So, like, if you think of, like, thunder, you have, like, a crack. It's like a crack, and then it's like a boom. So it's like, and then it's like, boom. So what's happening is the lightning is so hot that it burns basically a hole in the atmosphere. It's like ripping the atmosphere apart. So the initial crack of the lightning is the sound of the atmosphere exploding. Like, it's so hot that the air around it is expanding rapidly. But this creates a vacuum, and vacuums can't exist in nature. So what happens is that the atmosphere implodes on itself, and that's the boom sound. And this sound wave that it generates is the thunder you hear. The average length of lightning is 3 miles. The average width is 1 inch. The heat of the air around lightning is around 54,000 degrees Fahrenheit, and this is 5 times hotter than the surface of the sun. This is like my favorite fun fact, and when my professor told me this in Weather and Climate, I lost my mind. Like, I cannot even fathom what it would feel like to get struck by lightning. Like, something that is 5 times hotter than the surface of the sun. Like, it's just amazing that it exists. This is the longest recorded bolt. I don't think this is the picture of it. Maybe it is. I don't know, Science Mag. Okay, anyway, the longest recorded bolt in history. I don't think this is 110 miles. It's 118 miles near Dallas. Fun fact, on a clear day, you can see Dallas from the top of the National Weather Center. 5 to 10 strikes have enough energy to power a house for a year, but, like, how are you going to collect that? I don't know. If you can collect energy from lightning, you can become a very rich individual. So if you're interested in lightning and you're looking for something to do that will make you a lot of money, learn how to harvest electricity from lightning. 100 bullets strike the surface of the earth per second. Wow, that's a lot. 20 million bullets strike annually in the United States. That's also a lot. Lightning can strike the same place twice. Yeah, there's tall objects like the Empire State Building, etc., that can be struck by lightnings tens or even hundreds of times per year. Like, lightning has a preference. If it strikes a place one time, it's probably going to strike it again because it was attracted to it in the first place. On average, lightning kills the same number of people in the U.S. each year as hurricanes. I'm surprised it's so low in Oklahoma. I would expect it to be higher. But yeah, especially in Florida. Look at that, 49. I know there's a lot of people in Florida, but the lightning is really bad there. And people go to the beach, and it's like lightning. It's like, dude, like, I know it's your vacation, but it's going to be a bad vacation, like, if you don't go inside. The most fatalities is in Florida, along with the Gulf Coast and in the Southeast. There's just simply so many storms down here. Like, it gives you a lot of opportunities to be struck. Yeah, makes sense. Have hot spots for lightning fatalities in the U.S., but lightning and associated fatalities can happen anywhere. Well, I guess not in Nebraska or North Dakota or Washington or Maine or New Hampshire or Rhode Island or West Virginia or Alaska or Hawaii or American Samoa or DC or the Virgin Islands. I mean, they could happen, but it hasn't happened between 2009 and 2018, so don't be outside when it's lightning. If you can hear thunder, go inside for 30 minutes and after your last time you hear thunder. Anyway, let's talk about how lightning happens. So, they forgot to draw the ground. Why? Okay. Well, the ground's typically a negative charge, but in a thunderstorm, for whatever reason, the ground develops a positive charge. It's because these negative charges up here attract the positive charges to touch the surface of the ground. So, normally the ground is negative, but during a thunderstorm it's positive. Anyway, this is the brochure online where the temperature is 0 degrees Celsius. So, ice crystals, they have a positive charge and raindrops have a negative charge. So you have these positive charges up in the top of the cloud and negative charges in the bottom where this rain is. So, positive charge at the top of the cloud, negatively charged at the bottom. The bottom of the storm becomes more negatively charged because more water vapor condenses into liquid water, so you get more of these charges. So it builds up, and it's not evenly distributed. There's too many negative charges for the positive charges. So they have to go somewhere. Well, the surface of the Earth becomes positively charged. It loses electrons to strong storm winds that blow across it. I don't know if that's how it works. It says so on the PowerPoint. I can't verify that because I don't know. Maybe. I just don't think that... I would think that it becomes positively charged because this negative charge attracts positive charges to the surface of the ground. But I'm not a lightning expert. I only know what I know. So this could be true. This also could be false. You can Google it if it bothers you. I'll probably Google it. Anyway. That's not the important part. The important part is that the ground turns positive. Why it turns positive? Not as important. I'm sure it's important, but, you know, whatever. It turns positive. So the electrons flow from the bottom of the storm towards the surface. This is because you have positive charges here, and it wants to, like, even it out. It wants to, like, positive and negative charges attract each other. And these positive charges are kind of all taken, like they're all spoken for because these negative charges here are happy, like, but it's not balanced because there's more negative charges. So some of the negative charges move towards the ground. So it creates an initial current, and this is called a stepped leader. It literally looks like a ladder, but it's called a stepped leader. There's a small discharge. This is not, I wish it showed it a little bit better. What happens is these negative charges kind of form, like, it's like every 10 meters or so, you'll get, like, some negative charges right here, and then you'll get some negative charges right here, and you'll get some negative charges right here. And so it's like a negative and then a space, and then some negative and a space, and some negative and then some space. And then at the ground, you have a couple of positive charges that move up. The positive charges don't travel up that far, but they do travel up a little bit. So the stepped leader is the path that the light, all you need is like a little spark of static electricity or something to set this off, because you kind of have this battery going here. And what will happen is it discharges these negative towards these positive, and it will create lightning. And you can also get a positive streamer, which is these positive charges that strike, like, kind of like form a little upwards lightning. And some of my professors believe that you can't survive a lightning strike that comes from these negative charges, and most people that survive lightning strikes are just struck by the positive streamers. You can also get these positive charges to come down and form with the negative charges on the ground over here, or like wet ground, and create extremely powerful lightning. But that's for a different class. That's for like cloud physics or something. But yeah, you can get positively charged lightning, but it's rare compared to the negatively charged. Most of it is negatively charged lightning. So just a brief overview of what I just said. So these negative charges form in this step leader to the ground, and some positive charges move up towards the cloud. There's something that causes a discharge, like a little static electricity or something, and it causes this whole circuit to blow up and create lightning. So once the step leader and a positive streamer connect, electrons flow rapidly along this channel. So this is, on this, like the step leader just looks like this, but remember there's spaces. Like, wait, let's go back to the lightning picture. See, okay, so maybe there's some steps here, and then there's a space, and then there's like some steps here, and there's a space, and then there's some steps here, and here, and here, and here. That's why lightning kind of looks jagged like this, like the stepped leader is not in a straight line, and there's kind of spaces between them, so it travels between them, and it tries to find the best path down to the ground. Or you can also get lightning strikes because there's a positive and negative, so it's kind of like a battery. This is how you get that intra-cloud lightning. It will just create stepped leader from the top of the cloud, the bottom of the cloud to the top of the cloud, and you can get lightning. Or you can get it from cloud to cloud, so you can have like a cloud over here with some negatives, and it can connect to these positives, and it can discharge and cause lightning. Okay. So, I hope that makes sense. If it doesn't make sense, there's lots of videos about lightning. You can email me. We can have office hours. I can draw it for you. I don't want this lecture to go too much longer, but if you need help with lightning, let me know, and I can help you understand it more. So anyway, the electrons flow rapidly down this step leader, and the electric current is called the return stroke. It produces a lot of visible light because it is so hot. And this is the part of the process that we can see. So the return stroke is what you can see. Thunder happens as the return stroke rapidly warms and expands the air around it. So the speed of sound is 0.2 miles per second. For every 5 seconds between seeing the bolt and hearing thunder, the storm is an additional mile away. So if you see a bolt and you count 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, and then you hear thunder, that means the storm is a mile away. And so every 5 seconds you count is another mile. If you count 5 Mississippi and then you hear thunder, you should be inside. You do not want to get struck by lightning. You don't want to be a statistic on the weather and climate lecture. So why does lightning follow a winding path to the ground rather than a straight path? Isn't a straight path the most efficient path? Well, they have a source, so. Okay, wind deforms in the stepped leader and positive streamer, causing the bolt to bend. ABC News is the source? Okay, I kind of believe that, though. Aerosols, dust, sand, pollution in the air cause the step leader to turn, so a straight path is not usually the most efficient path to the ground. Yeah, exactly. So the step leader forms in the most efficient path to the ground, and I guess the aerosols and stuff, like, cause it to turn and take a different path to take the most straightforward path to the ground and not have to pass through things that don't conduct electricity well. So, yeah. They didn't talk about the steps. It is stepped, though. There are steps with gaps in the steps of the negative charges. Why does lightning have multiple branches? Electrons follow the path of least resistance, so they may more easily flow off to the side rather than straight towards the ground. So there's lots of different step leaders. So you could have like some negative charges here and some negative charges going this way and all over. So the negative charges branch out and it's trying to find the best path to get to the ground. Whichever one hits the positive streamer will be the path of the return stroke. So the electrons will flow down all paths, but if multiple step leaders make contact with the ground, the lightning will strike in multiple places. So if, let's say, like this branch here reaches down to the ground, then the lightning will strike in multiple places. Why does lightning hit tall objects? Because it's closest to the step leader. Everything gains a positive charge during a thunderstorm, including you. So positive streamers from taller objects are more likely to hit a step leader first. They're most likely, but not guaranteed, that the tallest object will be the one to get hit. The path to the object may not be the path of least resistance. So see the last slide. Are they going to show the picture of the dudes with their hair standing up? Okay, like, when you become positively charged and then you become connected to the step leader, like, you'll know when you're connected to the step leader because you will feel your hair rise in places that you did not know you had hair. Like, your hair will start standing up. If your hair starts standing up, like, crouch down, cover your ears, run. I don't know. I had one professor say to run. I had another professor. I don't know if running's the best option. I would probably run. But I had another professor say to crouch down, close your ears, and jump so you're not touching the ground. I guess that also makes sense. I would probably just freak out and run, but yeah. Just don't be outside, and then you won't get hit by it. You won't be the target of a stepped leader. That's easy. That's the easiest way to know what to do. So, we've talked about lightning emanating from clouds and hitting the ground. So, that's CG lightning, cloud to ground. Intracloud happens entirely within the cloud, so it's just the charge jumping between different charge regions of the cloud. This is most common, because remember there's positive charges at the top where the ice is, and negative charges where the water is. And then cloud to cloud is lightning that occurs between two or more separate clouds. Positive lightning, okay, this is what I was talking about. This is the rarer lightning, and it is so powerful. It is so loud. Like, it's insane. Positive lightning strokes are crazy. And they come out of the cloud like this from the side. Like, they'll come from the area where it's ice. Not water. So, lightning that starts from the upper positively charged region of the cloud. It only makes up about 8% of all lightning strikes. It's extremely dangerous. It can the charge can be 10 times greater than that of a negative lightning strike. So it comes out of the anvil of the cloud, which it can extend far away from the main storm. Yeah, so like this is why it's dangerous as well. Like it can strike far away from the storm. Like it's striking over here. The main storm is right here, but it's going all the way over here and striking from the side. So that's why, like, before the storm, if you hear thunder and stuff, like, you should go inside, even before you see lightning and before you see, like, the cloud directly overhead, because you could get struck with a positively charged bolt, and it's really not going to be a good scenario. And basically, the stepped leader I talked about, instead of being negative charges, is positive charges coming down, and then there's negative charges at the ground. So it's just reverse the process. Yeah, it can result in bolts of blue, lightning that strikes very far away from the main storm, where it may not even be precipitating. Yeah, so it looks like the lightning striking out of clear air, but it's not. It's just coming out of the side of the anvil. This is why you need to take shelter when a thunderstorm is even close to your location. You're less likely to get hit when you're far away, but if you do get hit, it will be far worse and more dangerous than getting hit from classic lightning closer to the storm. In my opinion, it's not going to be good either way, but yeah, it's really going to suck if you get hit by, you're not going to survive that, so. Heat lightning is not real. It just means lightning that you don't hear any thunder, but it's just too far away for thunder to be heard. And every lightning strike has thunder associated with it. You're just not in earshot. So, like, it may be up in the clouds, intracloud, and increase the distance. But heat lightning just means you can't hear the sound. But it's not real. So, if somebody starts talking about heat lightning or something, just be like, yeah, that's not real, sorry. Lightning safety, go inside. You're also pretty safe in a hard-topped vehicle if you're not if it's not an old vehicle. Because vehicles are like Faraday cages, so if the lightning strikes the vehicle, it will just go around the car instead of going inside the car, because it's metal. But don't be touching, like, metal objects in your car, or, like, be using a phone charging. Also, inside a house, like, don't be in the shower, don't use a landline phone, don't open your window, don't be using appliances. Even if it, like, you're using, like, a computer or something, anything plugged in can go awry. I mean, they say that you should unplug things. Do we unplug things? Not always. I don't charge my phone when it's lightning, because, I don't know, it just seems like a little too dangerous. But I will use my TV. But if my lightning does happen to strike my apartment complex, like, my TV's not going to work anymore if it gets struck. Don't take a shower in a lightning storm. Just wait. It's okay. You can wait. Yeah, it's safer to be in a vehicle than it is to be outside. Don't take shelter under a tree, on a hilltop, or in an open field that's open season for lightning because you're high up or you're touching a tree that's high up. If you can't get indoors or in a vehicle, go to the lowest area nearby and make yourself the smallest target as possible. Yeah, you don't want to be up on a hill or something. Like, just try to get in, like, a gas station or something. Like, I don't know. Don't be outside in a lightning storm. And I think that's it for today's PowerPoint. It's been about an hour and 15 minutes, so that's good. And I'll see you all next week.